Okay, we are at section 5.6, Newton's third law. And I've got a quick little demo here. I've got a balloon in front of me. I've blown it up, but I haven't tied it. I haven't tied a knot, so I'm just going to release the balloon. And now the cat wants to chase it. Why did I bring that demo in? Well, we're gonna see. Let's share the PowerPoint and look at this. If two objects interact, the force F12 exerted by object 1 on object 2 is equal in magnitude and opposite in direction to the force 2-1 exerted by object 2 on object 1. So force 1-2 equals the negative of force 2-1. Now I better hold on. I better pick that up before she eats it. Get away. Okay, I retrieved it. She won't eat it now. What does that have to do with the balloon? Well, as I released the balloon, the elastic membrane pushed all the air molecules out. So there's a force pushing the air molecules out, and there's an equal and opposite force pushing the balloon away. So you've got the molecules being ejected in this direction and the balloon ejected in this direction. That's what makes rockets fire. There's a force ejecting the heated molecules of a jet engine in one direction, or a rocket engine in one direction. It propels the rocket in the other direction. That's a very complicated example, but if you just push against the wall pushes against your hand. If you push against the table pushes against you. We see examples of the third law all the time. The very common expression is for every action, there is an equal and opposite reaction. That's how we say it in common terms. But let's repeat it. The formal definition: if two objects interact, the force F12 exerted by object 1 on object 2 is equal in magnitude and opposite in direction to the force F21 exerted by object 2 on object 1. F12 equals minus F21. So here, this is a gravitational example. You have two spheres, sphere 2 and the smaller sphere 1. So what's pulling 2 towards 1 is the force F12, and what's pulling the blue ball 1 towards 2 is the force F21, and F12 is equal to minus F21. They are equal, but they are in opposite directions. You can see that one is pointing downward and the other one is pointing upward. So the force of gravity is equal to the it's the force of the Earth on a projectile. Let's say you throw a football into the air. It's a projectile, so it goes up, but then it returns back because of the gravitational force. The Earth is pulling on the projectile. Guess what? There is the force of the projectile pulling on the Earth, and it's negative. It's the same magnitude, but it's in the opposite direction. Wait a minute, that doesn't seem to make sense. I mean, certainly the ball moves downward, but the ball moves downward, but the Earth doesn't move upward. Well, let's think about this. Let's share the iPad. And so let's just, you have the Earth, and you have this tiny little projectile. So we know that the force of the Earth on the projectile is equal to minus the force on the projectile on the Earth. So the mass of the projectile has a certain, force equals ma, Um, that's the gravitational acceleration. Let's just make it G. The mass of the projectile is affected by the gravitational acceleration, and that's equal to the force of the projectile, the mass of the Earth, and its acceleration. Well, let's exaggerate this. It's the mass of the projectile times gravitational acceleration, and the mass of the Earth, it's so much bigger, is a very little acceleration. See, the force is equal, but the mass of the Earth is so much greater that it causes a much smaller acceleration. It's negligible. There is an acceleration there, but it's negligible, and so we can ignore it. But there is a force there, the force of the projectile on the Earth. All right, let's go back to the PowerPoint. All right. Now, Newton's third law, you recall you used the force table. It was all about vectors, and we're going to continue to use vectors because they're a very good way of showing the force. And so there's a lot of here in A, you see there's a lot of subscripts. T is for table, M is for monitor, capital E is for Earth. So you see right there emanating from the black dot, you have an upper arrow. Well, first let's look at the downward arrow because we place the monitor on the table. And so there's a force of the monitor on the table. It's down. It actually comes from the gravitational force, Earth on the monitor. And we have a normal force, the table exerting a force on the monitor. Those are equal and opposite. The normal force, normal meaning perpendicular, so there's always a normal force, and it's perpendicular to the surface where the action is taking place. And besides that, the black dot, you have the force of gravity, Earth on the monitor, and you have the force of gravity from the monitor on the Earth. They're equal and opposite. But as we just discussed, the Earth is so much greater that you don't see the Earth. The Earth's mass is so much greater that you don't see the Earth move. And so on the side, or let's put in the equations. The sum of the forces is equal to the normal force plus the mg, the gravitational force, and they equal 0. Why do they equal 0? There's no acceleration. It's standing still on the table, so there's no acceleration. So the forces have to be equal. If there's no acceleration, the sum of the forces has to be equal. So the normal times j minus mg j is equal to 0. N equals to mg. The normal force equals to mg. Okay, so the normal, this is, this on B, you just see the forces, the normal force and the gravitational force. Now we're going to expand it, and at C, we're going to put a free body diagram. We have the normal force and the gravitational force downward, and they're equal and opposite in direction. And that's how we do a free body diagram. So we use these to calculate, and you'll see as we go on how we use these free body diagrams. Okay, if a fly collides with the windshield of a fast-moving bus, which experiences an impact force with a larger magnitude? The fly, the bus, or the same force experienced by both? What do you think? Well, it's the same is experienced by both. That's what we're talking about. We're talking about Newton's third law. Wherever there is a force, there's an equal and opposite force. So the bus is colliding with the poor unfortunate fly, and the fly is colliding with the bus. Not so poor and unfortunate for the bus. Now, which one experiences the greater acceleration? Now, remember how I did the projectile on the Earth. The mass of the bus is so much greater than the mass of the fly that the bus experiences very little acceleration, virtually none, and the fly experiences a very large acceleration. The ratio of the bus to the fly. So the fly experiences the greater acceleration. Okay, let's see. And that's it for this section. Next, we're going to do 5.7 analysis models using Newton's second law.